the day the curtain came down on a remarkable performer. Centre stage for the last time was PFR, the prototype fast reactor at Dounreay.
Nuclear scientists from around the world are meeting in the north of Scotland to mark the close down of what was once the world's most advanced nuclear power station. The Dounreay fast breeder reactor generates electricity from plutonium.
A multi-billion-pound dream of nuclear power has come to a dramatic end at the Dounreay plant in Caithness.
It's 20 years since the Caithness plant began providing power for the national grid. Nuclear experts gathered there today to witness the plug being...
PFR has played to a worldwide audience. E Caithnessia ad mundum, from Caithness to the world, says the Latin inscription at the entrance to the building that houses it. For Dounreay put Britain at the cutting edge of fast reactor technology. It led the world in advancing the skillful use of nuclear energy for peaceful purposes. With its smaller predecessor, DFR, Dounreay Fast Reactor, it demonstrated the feasibility of building large commercial fast reactor power stations. It broke new ground in fuel design. In terms of information and knowledge, its achievements are enormous. It is a job supremely well done by a team committed to the future. In human terms, Dounreay revitalized a community, created new jobs, bred new skills, rescued and stimulated the local economy. And yet, today it stands victim to the winds of change, a casualty of inaccurate predictions by those who, in the 50s and 60s, thought they knew what the world's future energy requirements would be. The world's growing number of nuclear power stations would need more and more uranium, they said, and that was already in short supply. The price would soar. It didn't. New sources were found. Far fewer nuclear power stations were built than was expected. The price plummeted. Nor did the world's need for energy soar in line with predictions. Prices rose after the 1973 oil crisis, and everyone used energy more efficiently. Those who predicted the future got it wrong. Today's nuclear power stations are based on thermal reactors, those in which neutrons from the fission process are moderated or slowed down. But these can only burn a small fraction of their uranium fuel, and they cannot efficiently burn plutonium, a byproduct of the uranium they use. In fast reactors, however, neutrons are not slowed down. They can burn the plutonium produced in thermal reactors, and as a huge bonus, they can also convert into plutonium the depleted uranium, which thermal reactors cannot burn. This is called breeding. Dounreay's first task was to demonstrate that a fast breeder reactor could be built and operated safely. So, in the late 50s, a great experiment started on the rock-bound coast of northern Scotland, midway between London and the Arctic Circle. If successful, fast reactors would provide for the first time an efficient means of extracting energy from plutonium under controlled conditions. The existing network of nuclear power stations could be supplemented by electricity from fast reactors. The cost of producing electricity would thus be significantly reduced. Fast reactors would, in fact, breed more atomic fuel than they consumed. The Dounreay fast reactor, DFR, was housed in a spectacular steel sphere which still dominates the site. Its 135-foot diameter, 3 feet greater than the Dome of St. Paul's, is the landmark by which the site is still best known today. In 1963, DFR, with a core not much bigger than a dustbin, became the world's first fast reactor to produce electricity for public use. By a strange paradox, hundreds of Highland crofts, which didn't even have a piped water supply, were now lit by fast reactor electricity. A special small thermal reactor, DMTR, was built to test the behavior, under irradiation, of materials intended for use in existing and future reactors. Fuel for this reactor and DFR was manufactured and reprocessed on the site. There were facilities, some of them the most advanced in the world, for handling and examining experimental fuels. and extensive laboratories with comprehensive test equipment and dedicated personnel. No other nuclear energy establishment in the world was so self-supporting or better equipped to carry through a reactor development program. DFR operated for 18 years until shutdown in 1977, when its role was taken over by the bigger 250 megawatt PFR. DFR had completed the task for which it was built. It had shown that a power-producing fast reactor could be designed, built and operated safely. It had given valuable service, both as a power station and as an experimental tool of worldwide repute. It had also provided a wealth of information for the design of the next plant in the fast reactor project, the PFR. It had shared its knowledge with the Europeans, Americans, Russians and the Japanese. If there was a measure of elitism in the air at Dounreay about this time, it was perhaps understandable. Willie Sinclair, a Caithness farmer's son, became a craft apprentice in 1956 and is now engineering services manager.
When I started work at Dounreay, it was exciting just to be part of such a new and important industry. The nuclear industry was at that time as fascinating and mysterious to the general public as space exploration became in the years that followed. Locally recruited people, such as myself, and the people who joined us from the south, atomics as they were called affectionately, we looked upon ourselves as being part of a very special technology. We felt we were way ahead of the world in fast reactor design, and as time went on, we proved the technology worked, and worked well.
The 250 megawatt PFR was to be a halfway stage between the pioneering DFR and the ultimate, a large commercial fast reactor with an output of at least 1,000 megawatts. Construction of PFR began in 1967, with the reactor going critical in 1974. Its first electricity reached the national grid a year later. PFR was another great stride forward.
The plant was designed to adequately represent the features of future commercial-sized fast reactors, for which it had to supply statistically meaningful information. The fuel consisted of mixed uranium and plutonium oxide, contained in multi-pin assemblies like this. The design of the assembly was sufficiently flexible to allow a large number of design changes during the course of the plant's life. The primary coolant was liquid sodium, and the plant contained features which would not normally be present in a commercial plant, such as the irradiated fuel cell, which allowed the examination of irradiated fueling components shortly after their discharge from the reactor.
In fact, most of the plant is located in one large building complex. The principal units in the power-producing chain, reactor, steam generators and turbine generator set, were arranged as close together as possible. This minimized pipe and cable runs and simplified staffing during operation, thus trimming costs. The performance of the reactor, its fuel and the sodium coolant were highly satisfactory. For some years, however, the power level and load factor for electricity generation were not high.
The problem was caused by minute leaks in the tube-to-tube plate weld on the evaporator units. This allowed small quantities of water to escape into the non-radioactive secondary sodium side. The solution to the problem was the fitting of sleeves which bypassed the weld area. In total, 3,000 sleeves were fitted over a period of 14 months. The solution was entirely successful, with a very dramatic increase in the load factor.
Safety is paramount, and the lead comes from the top. Station manager Ed Adam is in constant contact with his operations team and regularly tours the plant to discuss safety matters or any operational concerns that may have arisen. The safety team regularly monitor the environment in the reactor hall. PFR is highly instrumented with readings recorded onto paper trace charts and into the computer. Detailed data on operating characteristics, component performance, and the behavior of fuels and reactor materials has been recorded for future reference. There are facilities for dismantling fuel assemblies, examining and testing individual fuel pins, and reassembling them into rigs for further irradiation. PFR achieved its designed power output of 250 megawatts in 1985. A design then emerged for a 1,320 megawatt commercial fast reactor. The UK became involved with other European countries in a collaborative fast reactor agreement aimed at building commercial demonstration stations in France, Germany and the UK. However, the ending of the UK government's financial support for this futuristic project was just around the corner. The government reorganised the nuclear industry in 1987. In the following year, it was announced that support for fast reactor development had declined, a worldwide trend. Dounreay's innovative prototype fast reactor was to be phased out by the spring of 1994, and the fast reactor fuel reprocessing facilities were to be phased out 3 years later. Does this signal a decline in the fortunes of Caithness and its people? Change is constant. Progressive modernisation of farming methods in Caithness, as elsewhere, has boosted productivity but slashed manpower. Flagstone and slate quarrying, the main source of employment in 19th century Caithness, had collapsed, a victim of the widespread use of cheaper precast concrete paving. Overfishing had brought dearth to the North Sea, stripping the herring fleet to a fragment of its former self. In parts of the county, up to 19 children out of every 20 had no chance of earning a living in the community of their birth. The Caithness population, 44,000 in 1861, fell to 22,000 by 1953. By 1967, however, 67% of wage earners in Thurso worked at Dounreay. By 1990, many of the middle and senior management posts were held by personnel born or raised locally. Dounreay offered the rehabilitation that had eluded the county for so long. The population of Thurso spiralled from 3,200 to 9,000. At its peak, with PFR entering the scene, the establishment employed 2,400 people. Half were imported key staff, including a high proportion of professional and scientific personnel.
The impact of the plant was enormous. It brought massive numbers of new people to the area, people with new ideas who have contributed a great deal. The local authority built almost 1,000 houses, and the Atomic Energy Authority a similar number to cope with this influx. New hotels and new businesses were created. Now, unfortunately, we have the rundown of the PFR. But, nevertheless, the Caithness Fund and Highland Opportunity have both been initiated and funded by the local authorities. And I hope that those organisations will go a considerable way to stimulating new firms and new investment within our area.
As Dounreay begins the decommissioning phase of its life, there are hopeful signs that the local economy will remain buoyant.
Business too has benefited from the presence of Dounreay. A number of businesses have been set up by people who trained at Dounreay and developed their skills there and then left to go it alone. And then other businesses have grown up as subcontractors to Dounreay and have then gone on and looked for business elsewhere. A very good example of that is a company called JGC Welding, who did specialist welding work for Dounreay, but now have contracts all over the country.
The shutdown of PFR brings to an end, at least for the foreseeable future, the operation of fast reactor power plants in Britain. Over the last 35 years, numerous technical obstacles had to be overcome, but this was done thanks to the outstanding expertise and commitment given by everyone involved with the project.
A number of major engineering tasks were undertaken, including the replacement of the superheater and reheater tube bundle units and the evaporator sleeving. and the design and construction of a barrier to prevent seaweed entering and fouling the seawater cooling circuit for the turbine condenser. Dounreay also made a major contribution to knowledge about sodium-water reactions as they affect fast reactors. Supernova, a test rig, was built at Dounreay to investigate reactions under controlled conditions. And in 1987, an actual sodium leak in a PFR steam generator unit provided direct experience of what happens when sodium and steam meet under operating conditions. Perhaps the most significant obstacle arose in the summer of 1991. An oil leak contaminated the primary sodium circuit, a serious problem which closed the reactor for 18 months. To solve it, the PFR engineers were faced with the mammoth task of removing and replacing the primary pump filters, units which are normally immersed in the opaque sodium coolant. Many thought PFR would never start up again, but by the end of 1992, the problem was solved and PFR was back on power.
It was particularly appropriate that in its final period of operation, PFR achieved its highest load factor ever, and in its last year of operation set a new production record.
But the decision had been taken to shut down the innovative PFR on the 31st of March, drawing to a conclusion the UK government's fast reactor development programme.
But sadly, as you will all know by now, tomorrow will be the last...
On Wednesday, the 30th of March, Tony Broomfield, Reactor Services Business Director, welcomed over 200 people to a gathering at Dounreay to mark the occasion. Staff, past and present, many who had devoted the greater part of their working lives to fast reactor research and development, colleagues from other countries, registering the international contribution made by the UK programme, and representatives of the many companies who had supported the project. Sir John Hill, a former chairman of the Atomic Energy Authority, looked back at the fast reactor story with some humour, much pride and some regrets.
2 sites were considered for DFR, Speyside and Dounreay. When Speyside was visited, it poured with rain and blew a gale. It was declared unsuitable. When Dounreay was visited, the sun shone all day. It was declared an excellent site, and DFR was sited at the end of the runway. The economic environment of today does not, however, permit you or any other fast reactor team to go ahead with a full commercial plant. It is very sad, but it's a fact. It's also a fact that you cannot for too long keep a project running in neutral, and if there is no project of the next step taking place in a reasonable time, the people concerned become dispirited. Better to stop and pick it up again, or let your successors pick it up again when the climate has changed. PFR has been a great success. Over the 20 years in which it has operated, it has done everything that was hoped of it, and almost everything of which it is capable. It is a great pity that the government did not give it time to complete its job, particularly as it is now running so well and covering so much of its costs from the sale of electricity. It is therefore with great sadness that we have to accept that the time has now come for it to go into honourable retirement.
Tony Broomfield also had mixed feelings.
I personally don't wish to dwell on the decisions and the circumstances that have brought a premature end to this project, particularly at a time when so much is being achieved. Within the UK, we have always maintained close links with the nuclear utilities. We have benefited from the presence of attached staff from these companies, and for whose help we are grateful. With our colleagues in the European Partnership and in other countries pursuing fast reactor development that are here represented, we have maintained close links on operational matters. And today we have staff from France and Japan working at PFR. Staff from PFR have similarly worked overseas. And today we have 2 at the Monju site in Japan in the team in the final stages of taking Monju critical. The operations teams in the European Partnership have worked very closely together. With the EFR design teams and development teams, they have maximised the transfer of experience. The collaboration, in our view, has worked very well. Since 1978, the general public has been provided with the opportunity to visit PFR. Up to 7,000 visitors each year have taken up this opportunity. All of us engaged in nuclear operations must play their part in demystifying what we do and in reassuring the public of our confidence in the safety of operations. In this, the PFR team has played its part.
I would like to thank the PFR team.
Brian Eyre had further praise for the PFR team.
As has already been stressed today, we shouldn't underestimate the technical achievements, particularly those that have come out of our experience on PFR. They extend over a very wide range in understanding and managing irradiation damage problems such as void swelling and irradiation creep, in achieving outstanding fuel performance and demonstrating the complete fuel cycle, in understanding thermohydraulics and heat transfer problems, in developing sophisticated but effective instrumentation and plant condition monitoring systems, and in understanding the complex behaviour and failure processes in the materials used and developing effective solutions to those problems. And I could undoubtedly go on. We still have much to contribute. First, we must ensure that all of the knowledge and experience we've won is not lost. The information from PFR on the fuel cycle, on the experience of component and systems performance, and on the overall operating experience, all of this is particularly valuable. We must also make sure that the continuing information we'll get from PFR in the future is used effectively, from the reprocessing of the fuel, which will continue for some years, and in fact will provide unique experience in the recycling of high burn-up fast reactor fuel, and of course from the decommissioning programme. And we will also continue to exploit the technology, the accumulated technology that we've developed from PFR in other areas. And thus we in the UK will continue to make a significant and important contribution to fast reactor technology, and we must continue to maintain our links with our international colleagues. PFR is a prototype plant, and as such it's highlighted a range of technical problems and issues. This is a key aspect of operating a prototype plant. Many of these have been very novel and different issues from an engineering viewpoint. And I've seen at close hand over the last 12 years or so the work that's been done to address and solve these problems. And in my view, this has resulted in some of the highest quality and most innovative engineering I've seen. I believe also that the dedication and commitment shown by Ed Adam and his PFR team in implementing these engineering solutions has been absolutely outstanding.
Dr. Eyre, Sir John Hill and Station Manager Ed Adam joined a party of PFR personnel in the reactor's control room. The 12 long-serving members of the engineering and operations team, between them, represent 300 years of service at PFR.
This afternoon, PFR is operating at a power of 637 megawatts. Tomorrow evening, we have to shut down PFR and disconnect the turbine alternator from the grid. The process will take about 4 hours tomorrow evening. But this afternoon, we are going to start the lowering of the power of the reactor. And I'm going to ask the Senior Shift Manager, Gordon Blagden, to start that process.
The shutdown of PFR is a carefully planned, precisely controlled procedure. The mechanism for lowering each control rod is selected in turn on the control panel. The illumination of the buttons confirms that each command has been actioned. When all 5 control rods are primed, a 6th button is depressed to lower them. The rod's rate of descent is regulated manually by the operator. The gradual power decrease is monitored closely by the control room team. A poignant moment for a group of people who have dedicated most of their working lives to the innovative prototype fast reactor project.
The fast reactor project has been a success story, and PFR has made a substantial contribution by demonstrating the ability to achieve fuel performance in excess of twice the design target in operation of high-efficiency steam generator units and by generating over 9 billion units of electricity. Although the curtain has come down on the British fast reactor programme, operation of fast reactor plants continues in France with Phoenix and Super Phoenix, in Kazakhstan with BN350, in Russia with BN600, and in Japan, where the start-up of Mongju will mark the beginning of a new era. I am sure that future generations will require fast reactor technology for two reasons. Firstly, to generate power as fossil fuel stocks dwindle and the more efficient use of uranium is demanded. And secondly, to manage increasing plutonium stocks by using that plutonium as fuel, something fast reactors do efficiently. When the time comes to rekindle the flame in Britain, I am confident that those concerned will benefit greatly from the experience and knowledge gained over the last 35 years.